Good day, I'm Giancarlo Pineda and we will now be talking about the age of information through data compression. Let us first start off with the question, what is data compression? Well, data compression is the process of modifying or encoding the bit structure of data to ultimately consume less space in modern-day storage systems such as hard drives, SSDs, CDs, etc. The essential process of data compression is by eliminating any redundant or data present within the file by reforming these data strings for efficiency or by permanently removing them from the file. Now let us dissect data compression to its two most basic components. These two components are the encoding algorithm and the decoding algorithm. The encoding algorithm takes the file or message and generates a compressed version of the original file or message sent, while the decoding algorithm reconstructs the original message or recreates a close approximation to it from the sent compressed version. These two components are what completes the task of data compression since they have to both work together to understand the shared compressed file. Because of the integration of data in our lives, data compression is essential in one of the real-world applications that we always encounter, which is data transfer. With the use of data compression and data transfer, large file formats can now be compressed and be sent more efficiently to recipients using compressed formats such as zip and RAR files. Zip and RAR files compress large files into a smaller and much more manageable file size. By compressing files, it not only lessens the space taken up, but it can be archived more efficiently. Image and video formats are compressed using lossy data compression. Image and video formats tend to use lossy data compression techniques because of their large file sizes, wherein the process of reducing its file size is by removing or grouping together certain files together. Data compression and cryptography are similar because they both encode and decode data, but what is the difference between the two? Data compression's goal is to first of all reduce memory space by compressing and formatting files into compressed file formats such as zip or RAR. And secondly is to lessen transmission time of data. This in turn makes data transmission faster and more efficient. On the other hand, cryptography's main goal is to ensure security for the sender, the receiver, and the data itself by maintaining confidentiality, authenticity, data integrity, and non-repudiation. And of course, cryptography aims to make the sent data available to proper individuals that possess the permissions to do so, make it a secure and reliable way of retrieving data. Let us discuss the two types of data compression, which is lossless and lossy data compression. Lossless data compression has the ability to restore data to its original file version without experiencing any file loss while the file is uncompressed. While lossy data compression eliminates any redundant or unwanted data to compress said data, this is commonly used in graphics, audio, video, and image files where the files tend to be large. We will now discuss the kinds of lossless data compression methods. We will discuss Shannon-Fano code and run-length encoding as these are easier to understand and can be easily applied to basic file or message compression. The Shannon-Fano code is named after the creators of the code who are Claude Shannon and Robert Fano. This coding technique assigns various codes to each symbol based on the probabilities of occurrence. This is considered a variable length encoding scheme as the symbol has a varying length of code assigned to it. Let us discuss the steps in conducting Shannon-Fano code. This will comprise of 4 steps. We will start with number 1, which is to create a list by decreasing probability. In this slide, you are given the scenario, the symbols paired with its own relative frequency. The symbols are as follows. A equals 0.40, C equals 0.16, C equals 0.16, E equals 0.14, S equals 0.09, S equals 0.07. From the information, we now know the symbols which are A, C, C, E, S, S, and its respective frequencies. From there, we will arrange the symbols by their respective relative frequencies by decreasing order. We will then split the relative frequencies with both parts being as close to the equal probability as possible. In the table, we can see that the separation happened in between the two letter C's as the top half probability is added to get a value of 0.56 and the bottom half to get 0.46. Moving the separation anymore will make the value stray away from the equal probability. Now that the table has been segregated into 2 parts, we will now assign the value 0 to the top half and 1 to the rest of the bottom half. This will now be considered as stage 1 of the code. After stage 1, continue segregating part by part until splitting has stopped. A and C have been segregated to get a top of 0.40 and a bottom of 0.16. Thus, we get the values 0 and 1 for stage 2. Repeat steps 2 and 3 until we have segregated the symbols S and S. And once the splitting is stopped, we can clearly see the codes per symbol. A equals 0, 0, C equals 0, 1, C equals 110, E equals 110, S equals 1110, S equals 1111. Now, for run length, run length encoding is considered a very simple form of data compression wherein there is a given stream of data, which is considered as the input and output data stream, which is comprised of the number of times a letter has been enumerated within the data stream followed by the said letter that was enumerated. Here is an example data stream which spells chocolate, but it is comprised of 34 characters. We will compress it using run length encoding. First, we have to identify the letters that are present within the data stream, which is C, H, O, C, O, L, A, T, and E. Next, we will identify the number of times a letter has been enumerated within the data stream. Once we have identified the number of times a letter has been enumerated, we now have the compressed version of the original data stream, which is 6C, 6H, 3O, 1C, 7O, 1L, 2A, 4T, 14E. The compression took the 34-character data stream to a 19-character data stream just because of run length encoding. Now we will discuss the kinds of lossy data that we use in real-world applications such as JPEG and audio compression. JPEG is often seen today as a data format to compress photos, but it is considered as a compression method that compresses raw photographs taken from digital cameras into JPEG images that have a much smaller file size. JPEG compression is comprised of 5 main basic steps that make raw photos into JPEG images. First is RGB to YCBCR color space conversion. This converts the photo which is in RGB format into YCBCR color channels. Y is for the brightness, CB is the blue difference relative to the color green, and CR is red difference relative to the color red. Second is picture pre-processing, wherein the grayscale photo will be separated for 8x8 pixel blocks. This means that each block has 8x8 pixels and it is 64 pixels in one block. This causes a grid pattern on the image. Third is DCT transformation, which increases the effectiveness of the lossless encoding that will take place in the final step of the process. Fourth will be quantization of the image, wherein luminance and chromicness are quantized for the final encoding. And finally, the lossless encoding, wherein Huffman coding is used to compress the image. Audio compression is mostly used for various music and voice compressions. This can be seen in common file formats such as MP3, AAC, Windows, Media, Audio, and etc. Because of the wide use of audio compression, many different applications and audio formats have been made to compress audio. Thank you for listening to this topic on data compression.